Hello everyone, my name is Binh. Today I present the paper Gradient Alignment for Cross-Domain Phase Anti-Spoofing. So the paper is accepted in the CVPR 24 in Seattle, and I am from the DAS lab, which is supervised by Professor Simon Wu. So first, let me introduce about our lab. So our lab is data-driven AI security and human-computer interaction. And our supervisor is Professor Simon Wu. He associate professor, and he have several years working for NASA before coming to academic environment. And currently in our lab have 10 people in the doctoral degree and the other 18 master student. We also have open position for undergrad student. And the research area in our lab including data driving, which include anomaly detection, and we have several projects related to the Korean government. The second one is AI. So some topic related to is including the defect detection or metric learning. The last one is security and privacy, and we also have several papers published in the machine learning or adversarial defense or adversarial attack. And about myself, I have 4 years working under the supervision of Professor Simon, and currently I'm a PhD candidate. And in this summer, I'm working at Amazon at applied scientist interns. And more information about myself you can find in the link here. So about the conference, so the paper I'm gonna present today is accepted in the CVPR conference, which is the IEEE conference in computer vision and pattern recognition 2024. It was held in Seattle, Washington, and according to Google Scholar, as of 2024, this is the top 1 conference in computer vision and pattern recognition. And the outline of my presentation is first we have the introduction about the problem and some reverse conventional approach. Second one, I will present the methods, our proposed methods. Third one, we will present to you some experimental result. And lastly, we make some conclusion. I will go into detail of my presentation now. So let me first go to the motivation of the paper. The first point is that face recognition systems are vulnerable to representation attack. As you may know, some of your graphics device, for example, your mobile phone or laptop or iPad, usually using the face recognition system to unlock your phones or to perform some financial tasks, for example, transferring the money to your friend. And why they are vulnerable to representation attack? You can imagine that when attacker have some way access to your device, for example, they steal your phone, but they don't have your live face, and they some way take a photo of your face, print it to the paper, and so it's in front of your device, and then the face recognition system recognize that's your face, and then they unlock your phones. And this is very dangerous. And as you may remember, in several years ago, when the Apple introduced their iPhone X, and there is a group of researchers that have built a 3D face from just paper and the other material. And the cost to build the 3D face is just less than $150, and they already successfully unlocked the iPhone X. And the way to defend against that kind of attack is that you have to build a classifier model to classify whether the input phase is a live phase or the spoof phase. And phase anti-spoofing, or FAS here, is the problem we try to solve. But also you have to have a generalized domain, the generalized network that we call domain generalization. It means that your classifier not only successfully classify the live phase and spoof phase, but also it have to be generalized enough to predict the unseen attack methods. For example, it have you train your model in the with the data that only have the printed phase on the paper, but in the future there may be another type of attack to unlock your face recognition system using another mobile device or another material to build your face. That's we call domain generalization. And most of the conventional approach is that they build a additional module to classify the input phase. It come from the same domain or different domain. That's it to regularize the main model to be robot to domain shift. For example, you have a different training domain in your training phase, and the main loss is to classify the real or the live phase versus the spoof phase. And the additional module here is to classify whether two of the images come from the same or different domain. And usually they don't convert to local flat minimum. So why local flat minimum is important in the domain generalization? Because when you finally train your model, after some iteration, your model convert to a local point. In this point, your model does not change the loss significantly, and then you stop training. That's we call a local minimum. But for domain generalization, this local minimum have to be flat enough that whenever the input image is changed or the domain shift or different attack appear, you can imagine it change in the horizontal direction, and your loss have not to be increased significantly. But in this case, the step minimum, when the input just change a little bit and the loss already increased significantly, and this is not good for domain generalization. And how do we solve the problem? So in this paper, we develop a new objective function to encourage the model convert to the flat minimum with the additional learning module. This in the bottom figure is our robust method with a flat minimum. That's whenever the new domain introduced, the loss does not increase significantly compared to conventional methods. And additionally, we do not need the additional module here to classify whether the input image come from the same or different domain. But we introduce a regularization for the gradient during the training, such that the update in the different domain is aligned together. That's we call the gradient alignment for domain generalization in anti-spoofing, and we call our methods GAC FAS here. So let me first introduce some notation of our paper. For example, you have a learning neural network F with parameterized by a theta. So your neural network can be ALEXNet or ResNet, and the number of parameter. For example, you have 23 million parameter in the ResNet 50, and we call those parameter E the theta. And in your training data, you have different training come from different sources. We call it the both phase S here is the training data, and the SI different data set come from different collections, and K is the number of domain. And ERM objective is the empirical risk minimization objective. Why we call it empirical? Because we don't know where is uh, the optimal point of training a neural network. You have to rely on the training datasets, which is the S here, and you try to minimize the loss function by finding the optimal parameter theta. And in the training multi-short domain, we sampling dataset, different short domain dataset, and minimize the loss function with respect to each of the domain, and minimize them by update the parameter with some gradient descent algorithm, for example stochastic gradient descent or ADAM. So one of most related to our paper is that the subnet aware minimization paper. So the SAM try to minimize the perturbation loss. Why we call it perturbation loss? Because it adds some adversarial noise into the parameter of the neural network. You can imagine in this way. Usually you train a neural network, you want to increase the robustness of the model, so you gonna add in noise into your image or noise into your data to make the model more robust. But in this paper, they suggest to add in noise into the parameter of the network instead of the input data. And how the perturbation noise is derived is that they take the derivative of the loss function with respect to the parameter and normalize them and adding directly into the parameter of the network. And we call the theta plus the adversarial noise is the ascending point, because it makes the parameter of the network move to another point that makes the loss function increase significantly, and the theta has either ascending vector. And usually SAM-based approach have some limitation when applied to our problem. The first one is that when you derive the epsilon hat with respect to the whole training dataset, we gonna have the dominated epsilon hat, because during the training we gonna have several datasets, and some come from easy to learn and some come from difficult to learn. And dominated epsilon hat gonna make the training to be biased to some domain. For example, in this direction, we have 3 domains here, and the epsilon hat tend to bias to the domain S1. And the second point is that when you derive the epsilon hat with respect to each of the domain, you're gonna have the gradient conflict, because the epsilon hat here, when come from different domain, gonna go to different direction, and it's make the training is non-robust, and because there is confliction between the epsilon hat derived from different domain. And you can see the dashed blue arrow in the figure here at the final gradient update ascending point, translated to the current point of parameter theta t here. So to resolve the problem, our paper present a new objective to train the neural network. The objective, you have to satisfy some condition. The first one, you have achieve some update to the optimal minimum, which is the loss is sufficient low and reside in the flat loss surface. And the second one is we have to align the cross-domain gradient, that to generalization gradient update have to align with the empirical risk minimization gradient. And this is our loss function. So we go into one by one. The first one is the empirical risk minimization that I already presented in the 3 slides before. The second one is that the generalization, which look quite complex, but I'm gonna explain in detail in the next slide. And the last one is some regularization apply on the whole training dataset. For example, you can make the weight regularization or the distribution regularization over the training dataset. So we go into the benefit of our proposed method for domain generalization. The first one is that it makes the generalization gradient update and its empirical risk minimization gradient update. So let me rewrite the middle term in the slide number 10. You can rewrite the revert equation in this way. This is the expectation of the sub-training dataset, and the loss is the perturbation loss with respect to each of the domain, and you apply this perturbation loss for the whole training data, and then you minus to the dot product between the derivative of the perturbation loss and the empirical risk minimization loss. Let me show you how the regularization, the dot product here deriving. So for example, here the theta it has the model parameter at the training iteration t, and then 3 domain you have the ascending vector in different domain derived in this way, and then the first one is that the derivative of the loss with respect to each of the domain applied on the whole training data is the dash vector here is the gradient update at the ascending point, and then this dot product regularization make the update of the at each of the ascending point is the same direction with the empirical gradient update, which is the black vector here, and you can see that this regularization make the update at the ascending point to be the same direction with the empirical risk minimization gradient update. So we call this derivative term here in the first ingredient of the dot product is the generalization gradient update, and the second ingredient of the dot product is the empirical risk minimization gradient update. And here in this slide, we rewrite this regularization in another way. This means that the dot product between the generalization gradient update derived from each of the domain and the empirical risk minimization gradient update with respect to each of the domain. So in the experiment, we experiment with 4 different datasets: India relay attack, Occlu MPU, KCR, NFSD, and MSU MSSDs, and those datasets is collected from collected by different groups, and the subject in the dataset come from different people and different attack methods. For the backbone of the neural network, we just use a very simple neural network. That's the ResNet 18 for fair comparison with the reverse repose methods. And for evaluation, we use 2 metrics here. The first one is S-star, and the second one is AUC score. For those of you may not unfamiliar, so the S-star is the half total error is calculated by the average of the fail positive error and the fail negative error. In this problem, we refer to the positive case is the spoof phase, and the negative case is the live phase, which is similar with anomaly detection or in the medical classifications. And the AUC score is the area under the curve. The curve here is plotted by the true positive and fail positive case at different red hole, and the function gonna calculate the area under the curve plotted by that two criteria. And this is the experimental result. We have two main experiments here. The first one is leave one out experiment, and the second one is limited short domain. So for leave one out, we train with three different datasets and then evaluated on the other dataset and with two evaluation metric. And compared with the reverse approach, we have improved significantly on both of the metric across the dataset. For example, you can assert that we have the lowest Ester score and the highest IEC score. On the limited subdomain, we just trained with two domain and we evaluated with a single domain, similar with the left table. And we also observe our repose methods have the lowest Ester score in the two experiment, and we have the highest AUC score in the first experiment on MI2C. We also make another experiment on unseen attack. So unseen attack means that I train with 4 of those datasets and tested on unseen 2D and 3D attack. So each of the dataset is collected from different sources with the reverse 4 datasets. And we also observe that our methods have boosted the AUC score with up to 1% or 2% in both of the case compared to the reverse approach. So we further conduct one more ablation study in comparing the loss landscape of our repose methods compared to reverse baseline model. So how the loss landscape is calculated is that at the, for example, at the central point is the empirical loss of the whole testing dataset, and then we add in some noise to the testing dataset and calculate the loss again, and so on. So the distance from one point to the central point is to indicate how much of the noise is added into the loss, and the height of the loss landscape indicate how much the loss value increase compared to the central point, which means the clean data. And we can see that when to simulate the domain generalization, we saw that our repose methods in the last figure have the more flatter loss landscape compared to the reverse repose methods. It to demonstrate that our methods is more robust to the domain shift or of the change of the input image. Yeah, and finally, this is the conclusion of our paper. So we inspired by recent study about subnet-aware minimization, and we introduce a novel objective to optimize the minimum of domain generalization in the problem of phase anti-spoofing. And our repose method regulate the SAM generalization gradient of the whole data at the ascending point to be aligned with gradient derived from the empirical risk minimizations. And finally, we already conduct this comprehensive analysis across the dataset and evaluation setting, and we saw that our repose methods have improved the robustness of the model or more generalized compared to the reverse baselines. And thank you for your listening. And if you have any question, don't hesitate to contact me with the email in the first slide, and you can find our paper and the published code in the recording of the conference. And thank you again.